Bismillahirrahmanirrahim. Let us recall the definition of initial object in a category C. An object I in a category C is called initial object if and only if for any object A of the category C there exists a unique arrow from I to the object A. So we discussed the concept of initial object in our previous session. Let's prove a proposition regarding initial object. The proposition says that if I and I dash are both initial objects, if I and I dash are both initial objects, in a category C, then I is isomorphic with I dash. This means that initial objects are unique up to isomorphism. So let's prove this proposition. Note that since I is initial object, since I is initial, therefore there exists a unique morphism, a unique map from I to I dash. Since I is initial, so there exists a unique map from I to I dash. Let's call it F. Secondly, again, since I dash is initial, since I dash is initial, therefore there exists a unique map this time from I dash, because we are considering I dash as initial, so there exists a unique map from I dash to I. Let's call this map as G. So we compose these two maps by composing these maps. We have map from I to I dash. This is map F. Then we have map from I dash to I. This is map G, and we compose these two maps and we obtain a map from I to I. This is G composed with F. Now I is initial object, but I is initial, therefore there must be exactly one map from I to I. Therefore there must be exactly one map from I to I. But we know that there is identity morphism from I to I. But we know that identity map from I to I given by identity map on the object I always exists. Now there is exactly one map from I to I, and this is G circle F in this case, and we already know that there is a map from I to I which is identity map. Since this map is unique, therefore G circle F should be equal to this identity map. So therefore by uniqueness, G circle F must be equal to this identity map on the object I. And similarly we can prove that we can prove that F circle G is equal to identity map on the object I dash. So from 1 and 2 we conclude that from 1 and 2 we conclude that I and I prime are isomorphic. So initial objects are unique up to isomorphism. This is what we have established. Now we come to dual concept of initial object, and that is that of terminal object. So let's define what a terminal object is. So definition of terminal object. An object T in a category C is called terminal object. An object, let's denote it by T. An object T in a category C is called terminal object. If and only if for every object in C, for every object in C, let's denote this object by A. For every object A in C, there exists a unique map or unique arrow or unique morphism, there exists a unique map from A to T. So what we are saying is that for every object of the category C, there is a map from A to this particular object T, which we have defined as terminal object. To see what examples are, in set, the category of sets and functions, in set, the one element set is the terminal object. Any one element set let's denote it by this singleton. Any one element set is the terminal object. It is very easy to see. Suppose you have a set A and this is terminal object which contains only one element, and you can always define this map which takes every element of A to the star. So this map which takes every element of A to this single element star, this is the map we can always define. So from every set A, we can define a map to this set which consists of only one element. So this set is the terminal object in the category of sets. So secondly, in the category of groups, the one element group, that is the trivial group, is the terminal object. The trivial group is the terminal object. Let's have just a note. In the category of abelian groups, we denote it by AbGRP, the category of abelian groups. The terminal object is denoted by this group. In fact, you know that when we are working with abelian groups, the operation we use is symbol addition for the operation for abelian groups, and therefore identity element of an abelian group is denoted by 0. In general, we denote it by E. For abelian groups, we denote it by 0. Therefore, for the category of groups and group homomorphism in general, we denote the terminal object by this trivial group, and in case of abelian groups, terminal object is denoted by this trivial group. If operation is addition, we do use 0. If in general we use E. So in the category of groups, the trivial group is the terminal object. Now let's come to proposition. In fact, this is dual to the proposition we have already done for the initial objects. So let's have that proposition. If T and T dash are both terminal objects in a category C, then T and T dash are isomorphic. So if T and T dash are both terminal objects in the category C, then T is isomorphic with T dash. So for proof, note that the concept of terminal object is dual to the concept of initial object. So we note that the concept of terminal object is dual to the concept of initial object. And we have already proved that if I and I dash are initial in a category C, then I is isomorphic with I dash. We have in fact proved that. So we know that if I and I dash are initial objects in a category C, then I is isomorphic with I dash. We have in fact proved this fact in our previous proposition, and therefore by duality, T is isomorphic with T dash. Since if I and I dash are initial objects, then I and I dash are isomorphic, and concept of terminal object is dual to the concept of initial object. Therefore, by duality, if T and T dash are terminal objects in a category C, then they are isomorphic as well. So this is sufficient to say that since concept of terminal object is dual to the concept of initial object, so if there are two terminal objects in a category C, they are isomorphic as well. So having discussed initial objects and terminal objects, let's come to a concept which is based on these both concepts, and that is the concept of zero object. So zero object. Let's have definition first. So definition says that an object which is initial as well as terminal in a category C is called zero object. So an object which is initial as well as terminal in a category C is called zero object. Zero object in C. And zero object is mostly denoted by symbol capital O. The zero object is mostly denoted by this symbol. And the example of zero object, you already know that in the category of groups and group homomorphisms, the trivial group is initial object, and also the trivial group is terminal object. Therefore, the trivial group is zero object in the category of groups and group homomorphisms. So we know that the trivial group is initial in the category of groups and group homomorphisms, and the trivial group is terminal as well in the category of groups and group homomorphisms. Therefore, the trivial group is zero object in the category of groups and group homomorphisms. A category may not have zero object. For example, a category may not have zero object. For example, the category of sets and functions does not have zero object. And you know the reason why, because initial object in S in the category of sets, initial object in the category of sets and functions is the empty set phi, while the terminal object is the set containing only one element, singleton. This. So in this case, initial object and terminal object are different. So in the category of sets and functions, there is no zero object. So having discussed these concepts, let's come to an other concept of category theory, and that concept is called push out. So let's go to other page. In fact, we will need to draw a diagram in order to understand the concept we are going to discuss now, and we need little more space for that concept. So we are going to discuss the concept of push out. So in order to understand this concept, I will give you few examples as well. But first, let's have the definition of push out. So let's see be a category. So in a category C, the following diagram so in a category C, the following diagram, the diagram is like this. We have a morphism from object A to object B, and then from object A to object C. Let's call this F, and this map is G. Then we have a map from B to D and a map from C to D. Let's call this map alpha and this map beta. So this diagram is called push out diagram, is called push out. In fact, this is push out of F and G. Is called push out diagram if first of all we must have alpha composed with F is equal to beta composed with G. And secondly, for any maps, let me draw the diagram first. So we have this diagram. We have map from A to B, and that is F. We have map from A to C, and that is G. Then we have a map from B to D, that is alpha. We have a map from C to D, and that is beta. So for any maps from B to X, let's call this map as alpha dash. This is what we are saying. There is an object X, and if there is a map from B to X, alpha dash, and a map from C to X, let's call it beta dash. This is a map from C to X. We call it beta dash. If there are these two maps such that alpha dash composed with F is equal to alpha dash composed with F is equal to beta dash composed with G. Similar condition such that alpha dash composed with F is equal to beta dash composed with G. In fact, what we are saying is that if there are two maps satisfying the same condition, then there exists a unique map from D to X. Let's call this map theta. Then there exists a unique map from D to X. Let's denote it by theta, such that theta composed with alpha is equal to alpha dash. Theta composed with alpha is equal to alpha dash, and theta composed with beta is equal to beta dash. That is, this particular diagram commutes. So let me repeat the definition of push out. This particular diagram is called push out of these two maps if, first of all, alpha composed with F is equal to beta composed with G, and secondly, if there are maps from B and C to an object X which satisfy the similar condition. That is, if these maps are alpha dash and beta dash, then alpha dash composed with F is equal to beta dash composed with G. If this happens, then there is a unique map from D to X for which this part is commutative and this part is commutative. That means this diagram commutes and this diagram commutes. That is, theta composed with alpha is equal to alpha dash, and theta composed with beta is equal to beta dash. So this is the definition of push out, and this definition is very important. In fact, this concept emerges in several disciplines of mathematics, in theory of modules, in category of sets, in the category of groups, in the category of in fact, there are categories you might not be knowing, but anyway, we will try to understand this concept with the help of the categories we already know. And in order to begin with the examples, let's start with an example from the category of sets. So let's have an example from the category of sets. So in set, let A and B be sets in the category of sets. Let A and B be sets. Then the following diagram, I will draw the diagram on next page, is push out diagram. Then the diagram drawn on the next page is push out diagram. So let's see the diagram which we are calling the push out diagram in the category of sets. So we have two sets A and B. Let's take their intersection. A intersection B. And you know that A intersection B is subset of A. So there is a map from A intersection B to A which is called inclusion map. Let's denote it by F. Similarly, A intersection B is included in B, the subset of B as well. And we know that A is subset of A union B. So we have a map from A to A union B. This is again inclusion map. This is, let's call it alpha. This is G. And similarly we have inclusion map from B to A union B because B is also subset of A union B. Let's call this map beta. So what we are saying is that this diagram is push out diagram. What is the reason? Because you can very easily see that alpha composed with F is equal to beta composed with G. This is very simple to see because F, G, alpha and beta, these are just inclusion maps. So alpha composed with F is equal to beta composed with G. And secondly, if there is a map, if there are maps, in fact we need two maps as we have already defined. If there are maps from A to X, let's denote it by alpha dash, and from B to X, let's denote it by beta dash, such that, let's draw these maps first, then I will write the remaining conditions. So this is the diagram we are going to see, that this is a push out diagram. So this is the diagram A intersection B. We have a map from A intersection B to A which is F, and this is just inclusion map. We have a map from A intersection B to B which is G, which is again just inclusion map. Injection, this is injection in fact. And then we have a map from A to A union B, which is again inclusion map alpha, and we have a map from B to A union B beta, which is again inclusion map. So if there are maps from A to X, if there is a map from A to X, let's call it alpha dash, and there is a map from B to X, there is a map from B to X, let's call it beta dash, such that and you know the condition, such that alpha dash composed with F is equal to beta dash composed with G. Alpha dash composed with F is equal to beta dash composed with G. Then there exists a unique map. So this is what we have to establish, that then there exists a unique map, then there exists a unique map, a unique function in this case, in fact, a unique map from this particular object to X. This is the map we denote by theta. From this particular object A union B to X, theta, such that theta composed with alpha is equal to alpha dash, theta composed with alpha is equal to alpha dash, and theta composed with the beta is equal to beta dash, and theta composed with beta is equal to beta dash. So this is what we have to establish. We simply have to give the definition of this particular map theta, what this map theta is going to be. So we define theta as, so this is the way we are going to define theta, and this is the definition of theta: effect of theta on any element of A union B, let's take that element as Y, is equal to effect of alpha dash on Y if Y belongs to A, and effect of theta on Y is equal to beta dash Y if Y belongs to B. Note that since Y is going to be an element of A union B, therefore Y will either belong to A or Y will either belong to B. So if Y belongs to A, then define theta Y is equal to alpha dash Y, and if Y belongs to B, then define theta Y is equal to beta dash Y. So this is the way we define the map theta, and it is very easy to verify the conditions that theta composed with beta is equal to beta dash, and theta composed with alpha is equal to alpha dash. It's very easy to verify these conditions. So let me simply comment. You must verify that theta composed with alpha is equal to alpha dash, and theta composed with beta is equal to beta dash. And it is very simple to do that because your maps are simply just inclusions. This is just inclusion, this is these are inclusions, so you will be very easily able to see that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. So having done that, having discussed an example of push out from the category of sets, let's come to another example of push out, and in this case we take this example from the category of abelian groups. So let's take another example. So in AbGRP, that is category of abelian groups and group homomorphisms. So let's consider this particular category. In this category, the diagram I am going to draw now is push out diagram. The following diagram is push out diagram. So since we are considering the category of abelian groups, and we know that in the category of abelian groups the trivial group is denoted by 0. In general we denote it by E, but in abelian groups the identity element is denoted by 0. So this is trivial group, and we know that given any two groups A and B, there is a group homomorphism from 0 to A, and if we are given another group or a group B, there is a group homomorphism from this trivial group to B, because trivial group is initial object in the category of abelian groups. So in general I must correct myself. Trivial group is initial object in the category of groups, and therefore in the category of abelian groups trivial group is initial object as well. So if there are two groups A and B, there is a unique map from this trivial group to A and a unique map from this trivial group to B. Let's take these maps as F and G. So we are going to have Pushou diagram of F and G. So it is important thing to have what object we are going to have at this place. So at this place we are going to have this object A plus B. This is direct sum of A and B, and this very simple group, you know that this is just the Cartesian product of A and B with certain universal property, but it is very easy to see that elements of A plus B are order pairs whose first elements are from A, second elements are from B, and binding operation is given point wise, and everything works very well, and you know this construction very well. So we have map from A to A plus B, let's call it alpha, and a map from B to A plus B, and let's call this as beta. You are very much familiar with these two maps, alpha and beta, from A and from B. So the following diagram is push out diagram, because now we are going to give the reasons. Because first of all, you can very easily see that if we compose alpha with F and we compose beta with G, these two are going to be equal. It is very easy to see, and you must work it out that alpha composed with F is same thing as beta composed with G. Very simple thing, but it is an exercise for you. And secondly, if there are maps maps in case we mean group homomorphism. If there are maps from A to X, we denote it by alpha dash, and from B to X, we denote it by beta dash. Before writing what we have to write, let's draw the diagram first. So this is the trivial group, then we have a map from trivial group to A, because trivial group is initial object. We have map from trivial group to B, because trivial group is initial object G, and we have a map from A to A plus B, which is direct sum of A and B. We have map from B to A plus B, which is direct sum of A and B, and this map is alpha and this map is beta. So if there is an object X and a map from our group homomorphism from A to X, alpha dash, and a group homomorphism from B to X, that is beta dash, such that alpha dash composed with F is equal to beta dash composed with G. If there are maps this and this, let me write it here, such that alpha dash composed with F is equal to beta dash composed with G. Then there exists a unique group homomorphism from A plus B to X, let's write it as theta, such that this diagram commutes and this diagram commutes. That is, theta composed with alpha is equal to alpha dash, and theta composed with beta is equal to beta dash. So if there are maps from A to X and from B to X such that these conditions are satisfied, then there exists a unique Then there exists a unique group homomorphism from A plus B into X map from direct sum, in fact I must say direct sum of A and B to X, we denote it by theta, such that theta composed with the alpha is equal to alpha dash, and theta composed with beta is equal to beta dash. Let's call these as 1. So important thing is to demonstrate what this particular map theta is going to be. So let's see what this theta is going to be. So we define this map A plus B direct sum of A and B to X theta as follows. Note that theta is going to be a map from this direct sum to X, and I have told you that elements of this direct sum are just order pairs whose first elements are elements of A and second elements are elements of B. So this is a set of order pairs, in fact. So effect of theta on a typical element of A plus B, direct sum of A and B. Let's see what that is going to be. Effect of theta on AB. Remember that AB is an element of this direct sum. So effect of theta on order pair AB, we define it as this is equal to effect of alpha dash upon A and then effect of beta dash upon B, and then we add these two with each other. Let me show you what we are saying. Order pair AB is an element of this direct sum and A is element of A. So you just take effect of this group homomorphism alpha dash on A. This will be an element of X, and X is an abelian group, this category of abelian groups. And then this element B is element of this group, abelian group B, and beta dash has domain as B. So take effect of beta dash on this element B. This will be an element of X. X is an abelian group. Alpha dash A is in X, beta dash B is in X. Therefore, we can add these two with each other. So this is the way we define theta, and it is for you to verify that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. So for you, verify that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. So having done that, and if you do a little bit more effort and prove that this theta is unique, then the diagram we are discussing will become the push out diagram. So verify this, and secondly also verify that theta is unique. That means this is the only morphism which can make these things happen. So this was an example of push out from the category of abelian groups and group homomorphisms. Now let's come to another example from the category of left R modules, or we can have another example from the category of sets. So let's have an example from the category of sets, then we will see other examples. Category of left R modules, and so let's see an example from the category of sets. So in the category of sets and functions, in this particular category, set, this is the category of sets and function between sets. So in sets, the following diagram let me draw the diagram. Diagram is push out diagram. So we are going to have a set A and a function from set A to set B, and call this function f, and a function from set A to set C, call it G. In fact, these are the functions on which we are going to define the push out. These are the functions we begin with, and these things come later. These are in fact, this object is for push out object mostly. So we begin with these two morphisms, with these two maps, and then the object we define at this particular place is the push out object, this one. So how we are going to obtain this particular object? Note that we are going to denote the object, this object, as disjoint union of B and C. You know what disjoint union means, but this is not only disjoint union, it is more than that. So just to emphasize, I am going to put dot here. So this is disjoint union, but a bit more than that. I will tell you what does this mean. So we have a map from B to this disjoint union, call it alpha, and a map C to this disjoint union, a bit more than disjoint union anyway, call it beta. Now let's see what this particular object is, where this where this is the disjoint union of B and C, is the disjoint union of B and C, union of sets B and C with elements FA and GA. Identified for each A belonging to A. Now, this is very important thing to note. This is a disjoint union of B and C, but if for some element of A we have an element FA in B and we have the element GA in C, then FA and GA will be identified. That means that they will be only one of them will be written. Either you will write FA or you will write GA, or FA is equal to GA sort of thing. So we will identify the elements FA and GA for each element A belonging to A. Anyway, this is push-out diagram. Let me put it in bracket because this was not part of our scheme of proofs. I have simply tried to explain that what this object is going to be. So I have explained about this object. Now we have to show that this diagram is push out diagram, and now we are going to give the reasons because, and you know that the first part of our reason is alphas composed with F is equal to beta composed with G, beta composed with G, and you can very easily see that. So you can very easily see it. Or you must try to see it. So first of all, alpha composed with F is equal to beta composed with G. So alpha composed with F is equal to beta composed with G, and secondly, if there are maps from B to X, we denote it by alpha dash, and from C to X we denote it by beta dash, such that you know the conditions. Let me draw the diagram first. So note that we have function from A to B, we have function from A to C, this function is F, this function is G, and then we have this map alpha to be sort of disjoint union C, and map from C to this is beta. Now if we have maps from B to X, let's write object X somewhere here. So if we have map from B to X, this is alpha dash, and map from C to X, this is beta dash. then we have to prove that there is a unique map from here to here, call it theta, such that this part commutes and this part commutes. So such that alpha dash composed with f is equal to beta dash composed with g so we have to define this map. Then there exists a unique map from this disjoint union to x denoted by theta, such that theta composed with the alpha is equal to alpha dash theta, such that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. We define theta in this way, that theta, effect of theta on any element of this particular object. Suppose we see effect of theta on element y of this object, then effect of theta on y will be equal to alpha dash y if y belongs to B. Remember that elements of this object are either the elements of B or the elements of C. So effect of theta on y will be equal to alpha dash y if y belongs to B, and effect of theta on y is equal to beta dash y if y belongs to C. So this is the way we define theta, and it is very easy to see that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. This is what we had to prove. In fact, we have to define theta in such a way that these two conditions are satisfied, and this can be seen very easily that these two conditions are satisfied. Further, theta is unique, can be seen very easily. Therefore, the diagram we started with on the previous page is push out diagram. Next, we come to examples of push-outs in the category of left OR modules. Push-outs in OR mod, that is the category of left OR modules where R is a ring with identity. So before giving examples of push-outs in the category of left OR modules, let's note a very simple thing. So let us consider two module homomorphisms. So let F from A to B and G from B to C be module homomorphisms. In the category OR mod, category of left OR modules. So then we can very easily see that this particular set, that is set of order pairs FA minus GA, which belongs to direct sum of B and C or co-product of B and C. For A belonging to A varies over elements of A. Then this particular set, let's call it S. This is submodule of B plus C, is submodule of B plus C. It can be verified very easily. It can be easily verified. Let's note that where this particular object is in fact direct sum of B and C. Direct sum or co-product in the category of left arm modules is direct sum of B and C. So S is submodule of direct sum of B and C. Therefore, we can define quotient of this direct sum with S, quotient module, and let's name it as D. Then we claim that the diagram, this diagram, this is morphism F, this is morphism G, and that this is morphism alpha, and this is morphism beta. Let's see what alpha and beta are, where alpha, effect of alpha on any element of B is given by B zero order pair plus S. That is the coset of S with B0, and effect of beta on any element of capital C, let's write it as C, is given by 0C plus S. That is coset of S with 0C. So these are the way we define module homomorphisms alpha and beta, and we claim that this particular diagram commutes. So to prove that, let's see how do we prove it. So we have to prove that alpha composed with F is equal to beta composed with G. So to see this, let's see the effect of alpha composed with F on element of capital A. So we note that alpha composed with F effected upon an element A of capital A is equal to effect of alpha upon FA, and we know the way alpha is defined. This is equal to FA 0 order pair plus S by this definition, and effect of beta composed with F on an element, effect of beta composed with G, sorry I'm writing this, effect of beta composed with G, beta composed with G on an element of A is given by effect of beta upon GA, and effect of beta is given by this relation, and this is equal to 0 GA order pair and its coset with S. Now, having done that, note that difference of these two order pairs FA0 and A0 0GA, difference of this order pair and this order pair, difference of these two order pairs is equal to FA minus 0 is FA, and then 0 minus GA is minus GA, and we know that this particular element belongs to S. This belongs to S, and therefore coset of this particular element FA0 minus 0 GA plus S is equal to S, because this element belongs to S. So coset with this particular element of S is equal to S, and therefore we take this minus 0 GA to the right hand side. So therefore FA0 plus S is equal to 0 GA plus S, and therefore by definition this is equal to alpha composed with F effected upon A, and this is equal to beta composed with G effected upon A. Let me show you. FA0 order pair coset of this with S is equal to alpha composed with F effected upon A. So this is equal to alpha composed with FA, and this is equal to beta composed with G effected upon A. So this is equal to this, this is equal to this. This is what we have written, and therefore this is in fact for all elements A belonging to A, and therefore alpha composed with F is equal to beta composed with G. And so we have proved that this particular diagram commutes. So having done that, let's come to an example of push out in the category of left R modules. So let's have the example. Example of push out. In the category of left R modules. So we will have more than one example. So examples. First example. Example 1. It is the same we have just discussed right now. So let F from A into B and G from B into C be module homomorphisms. Let F from A into B and G from B into C be module homomorphisms. In the category of left R modules or mod. Then we have just discussed that, then we know that this particular set we denoted it by S. This is equal to set of order pairs FA minus GA belonging to direct sum or co-product of B and C for A belonging to A is submodule of, this is submodule of, we have commented about this in our previous case. So this is submodule of this co-product B plus C, a direct sum B plus C. So we can factor this direct sum with its submodule, which is S. This is quotient module and we denote it by capital D. So let's say it capital D. Then we claim that then the following diagram this is the diagram we are talking about. Morphism from A to B, which is F. Then morphism from A to C, which is G. So this is G. And then we have map alpha to D, this quotient module, and then from C to D, beta. Then the following diagram, this particular diagram is push out push out of in fact these maps F and G. F and G. So this diagram is push out diagram. I have made little mistake here. F is a map from A to B, it is okay. And G has to be a map from A to C. This is I am making mistake here, so please let me correct it. G is a map from A to C. Please correct it in your notes as well. Because if you do this, then this is defined because F has to effect on elements of A and G has to effect on elements of A as well. I just made a slight mistake here. Please correct it. Anyway, so we have to prove that this particular diagram is push out diagram, push out of F and G. So let's have proof for this particular proposition. So in order to prove that this is push out diagram, first of all we have to show that alpha composed with F is equal to beta composed with G, and we have already seen this. So first of all we have already proved that alpha composed with F is equal to beta composed with G. So our first condition is automatically satisfied. Now suppose there are maps for our second condition. Now suppose there are maps means module homomorphisms. There are maps map from B to X, which is alpha dash, and map from C to X, which is beta dash. Suppose there are maps in the category of left arm modules such that alpha dash composed with F is equal to beta dash composed with G. Let me draw the diagram. So we have maps from A to B. This is F. Then we had map from A to C, and this is G. We have D here, which is in fact quotient module, B plus C, co-product B plus C factored with S we have already discussed, and we have these maps alpha and beta, and we have discussed these maps alpha and beta in our previous note. Now suppose there are maps from B and from C to this object X. These are maps alpha dash and beta dash such that alpha dash composed with F is equal to beta dash composed with G. Then we have to prove that we have to establish that there exists a unique map from D to X we denote it by theta. Unique map from D to X theta such that this map has to be such that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. So this is what we have to establish. In fact, we have to define this map theta so that these conditions are satisfied. These conditions. So let's see how we define this map. So we define theta as follows. So we have to define effect of theta on elements of D. And elements of D, you must be knowing that D is in fact quotient module, quotient of co-product of B and C with S, and we have already discussed what S is. So a typical element of D will be of this form: BC coset of BC with S, or coset of S with BC. So this will be a typical element of D. So we have to see effect of theta on this, and this is the way we are going to define this effect. Note that B belongs to this module B. So we can have effect of alpha dash on B. So we can have effect of alpha dash on B. Also C belongs to this module C. So we can have effect of beta dash on C. Now these two elements alpha dash B and beta dash C belong to this module X. So we add these two elements in the module X. So this is the way we define theta. Now you can easily verify that theta composed with the way theta we have defined, theta composed with alpha is equal to alpha dash, and theta composed with beta is equal to beta dash. It is very easily visible. I was just explaining the same thing and you can see it very easily, and that This is the only map for which these two things happen, and that theta is unique. So you can see it very easily. So having done that, we have therefore established that the diagram we started with is push out diagram. Therefore, let me draw the diagram we started with. It was in fact this part of the diagram. A to BF, A to CG, and then we have alpha, and then we have beta, and this is D. Therefore, this is push out of F and G. Push out at F and G diagram in the category of left OR modules. So this was an example of push out in the category of left OR modules. We can have another example of push out in the category of left OR modules, and this is very simple one. Another example. Another example of push out. In the category of left OR modules. So for this example, let us consider a left OR module M. So in the category left OR modules, let capital M, let capital M be a left OR module. Be a left OR module, and let B and C be submodules of M. Be submodules of M. And let us consider the sum of these two submodules B and C. Sum of these. This is sum. In our previous example, this was direct sum, which was co-product. But in this case, B plus C is sum of submodules in which we take one element of B and one element of C and we add those two elements with each other. And you are very familiar with this definition. So let sum of these two submodules be denoted by D, capital D. I simply repeat, this is sum of submodules. In our previous example, that was co-product of modules or direct sum of modules. This is sum of submodules, so they are different. And you must consult your previous books and previous lectures you have already taken on theory of modules. Anyway, so let D is equal to B plus C, where B plus C is sum of submodules B and C. So D is sum of submodules B and C. Then this is what we claim. Then we claim that this diagram B intersection C inclusion map to B, then B intersection C inclusion map to C. These are very simple maps. Let's call it F and let's call it G, and then this map from B to B plus C and from C to B plus C, let's call it alpha and let's call it beta. These maps alpha and beta, very simple maps. We will define these maps very soon. So then we claim that this particular diagram is push out of F and G. So this is push out diagram. This is what we have to establish. So in order to establish that, first we note that what is the definition of alpha and beta. We note that alpha and beta are given by effect of alpha on any elements on any element of B. Let's write small b. So effect of alpha on an element B of capital B is equal to B plus 0. In fact, this is just B. And effect of beta on any element of C, let's write it as C, is equal to 0 plus C, and this is equal to C. Now it is very obvious that alpha composed with F is equal to beta composed with G, because these are just inclusion maps and alpha and beta I have just explained. Then it is obvious that alpha composed with F is equal to beta composed with G. It is just obvious. So this condition is very easily established. We come to next condition, and for that we have to consider two maps from B to X and C to X, and then we have to define a module homomorphism from D to X so that the particular condition is satisfied. So secondly, let from B to X, this is what we call alpha dash, and from C to X, this is what we call beta dash. So let alpha dash and beta dash be module homomorphisms. in the category of left arm modules, such that I write condition here. I will draw the diagram on the next page, such that alpha dash composed with F is equal to beta dash composed with NG, and you will be able to see that when I draw the diagram. So this is the diagram. First I draw the push out diagram, which we have to establish, that is push out. So this is the map from B intersection C to B, which is just the inclusion map, and then from B intersection C to C, which is again the inclusion map. We denote it by F, we denote it by G, and next we have got sum of these two sum modules B and C. B plus C, we denoted it by capital D, and we have these two maps. This is alpha, which takes any element of capital B to itself, in fact, in D, and similarly we have this map beta, which again takes any element of C to itself in D. Any small b goes to b plus 0, any small c goes to 0 plus c. We have defined it already. And if there are module homomorphisms from B to X and from C to X, this is alpha dash and this is beta dash, then we have to prove that there exists a unique module homomorphism from D to X theta, such that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash. So I have written that already, that alpha dash composed with F is equal to beta dash composed with G, and if there are module homomorphisms alpha dash and beta dash, so that these conditions are satisfied, then we have to establish that existence of module homomorphism theta from D to X in the category of left arm modules, such that theta composed with alpha is equal to alpha dash and theta composed with beta is equal to beta dash, is equal to beta dash. Now let's see how we define this map theta. So we define theta as follows. So domain of theta is D, and D is in fact B plus C. Let me write it here for ready reference. D is equal to sum of these two submodules B plus C. So effect of theta on an element of D, this is what we have to see. effect of theta on an element of D, and any element of D is sum of one element of B and one element of C. This is the definition of sum of submodules. So a typical element of D will be of this form: B plus C, one element of B plus one element of C added with each other. So effect of theta on B plus C is equal to, this is the way we define it. Note that B belongs to this submodule B, capital B. We can take effect of alpha dash on this B. This will be an element of X. So this is equal to alpha dash B. This is the element of X, alpha dash B. And then we can see effect of beta dash on C, because domain of beta dash is capital C and this small c is element of capital C. We can take effect of beta dash on small c, and beta dash c is again in X. So this is the element of X, this is the element of X. We can add these two with each other. So this is the way we define theta. Now it is very easy to see that. Then it is easy to see that theta composed with alpha is equal to alpha dash, and theta composed with beta is equal to beta dash, and also that theta is unique. So having said that, we have established that this particular diagram is push out of F and G diagram. Therefore, one is in fact this part of the diagram. One is push out of F and G diagram. So this is another example of push out in the category of left OR modules. So having said that, having seen quite a few examples of push outs in few categories, in fact there are many examples of push outs in other categories as well. It all depends upon your interest and upon your knowledge. Let me write few more examples, and if you are interested you can search for these examples in the library, on the internet, and it all depends upon your background. So few more examples of pushouts. Few more examples. Of pushouts. I repeat it again. These examples depend upon your interest. Depending upon your interest or depending upon your background. So the first example, in the category of groups, in GRP, the category of groups. Free product with amalgamation. Free product with amalgamation. Amalgamation. This is an example of push out. Secondly, in the category of abelian groups, direct sum with gluing. Direct sum with gluing. This is an example of push out. And thirdly, in the category of topological spaces, adjunction space is an example of push out. Adjunction space. This is example of push out. And in the category of commutative rings, CRNG, commutative rings with identity. In fact, just note that. So in this category, tensor product of rings, is an example of push out. I have written these examples just for your interest. If you are interested, you can go to library and search for these examples in books, or you can search these examples on internet. In fact, all depends upon your background. If you have studied group theory quite deep, you might be able to recall this concept. You may be able to recall this as well, topological spaces, but it may be the case that you might have not studied group theory or topology or ring theory so deep. But even then, if you have some knowledge of these concepts, you can try on your own and understand these push outs very easily by a little bit effort.